All right. So last time where we left off was we were trying to understand like the decision space of an LP. So just to remind you, LP is essentially you want to minimize this sort of objective function, a linear objective function. Here, xi's are decision variables. And we said, okay, we will differ talking about like the simplex method or standard solutions like for a later time. Before that, we want to understand the decision space as well as we can. And typically, the decision space looks something like this: B1 and AM1x1, AMnxn less than equal to Bm. And this is what we're concentrating on right now, understanding what is the structure of the decision space. And for that, we defined a series of things like affine sets and convex sets. And the relevance was if some of these inequalities were equalities, they will give rise to some affine sets. So affine sets are nothing but translates of subspaces of Rn. Yeah, so and convex sets, when you have these linear inequalities, you end up with examples of convex sets, which are closed under the following operations. So this set K, so if it is convex, then if I have 2 points in K, then the line segment joining both, so it doesn't quite look like a line segment. So uh, so just pretend it's a line segment. So then the line segment is completely lying within K. If for any two such points in K that happens, then it is a convex set. And a very standard example of a non-convex set is you put this sort of inward curved thing, so that if you take 2 points here, you have the line segment joining these two, and some part of it lies outside this set. So K is not convex. All right, and the relevance to LP, as I said, when you have linear inequalities, your decision space will become convex. All right. So we'll continue. We have one more thing to say. I had mentioned there are three things: affine sets, convex sets, and cones. And then we'll wrap them together with their relevance to linear programming. So cones in Rn. So cones, a set C in Rn is said to be a cone, and it precisely like visually means what you expect it to mean. Said to be a cone if for every x in C, if for every x in this set C and a non-negative number theta, we have the scaling of x by theta actually lies again within C. In other words, C is closed under this operation of scaling by non-negative numbers. So in particular, 0 will be there. If I choose theta is 0, 0 acting on x is again giving you the 0 vector. So 0 vector is always in any cone. So visually, you can think of it this way. So let's say this is the origin, 0 vector, and look at this region. So this is in fact a cone. Typically, you would think that what about this region? So even if you ignore this region, so this is like some sort of course, I wouldn't say it's quite disconnected because all of it is connected at the origin, but you can think of it that way. Typically, you think of a cone like this. This is what is known as a convex cone. This example on the left. Right-hand side is a general definition of a cone. So if a set is a cone and also convex, then it is called a convex cone. Not yeah, not too hard to imagine. That would be the definition. So let me write it out. A set C in Rn is said to be a convex cone.
Sir, can we have example of cone where cone is not convex?
This is the example I give. So you have, let's say this is a convex cone and you take another convex cone and in between there is some gap. So this is a cone, right? I'll redraw it. Let me finish this definition. I'll draw that example. Uh, yeah, set C in Rn is said to be a convex cone if it is convex and a cone, which means that for any x1, x2, if we have 2 points x1, x2 in C, and two coefficients, theta 1, theta 2, which are non-negative, then that then a linear combination, this theta 1 x1 plus theta 2 x2, also belongs to C. In particular, you just recall the definition of convexity. What happens? You want theta 1, theta 2 so that the sum is 1. So that condition we are not even demanding here. So of course, this C is going to be convex if we have this definition. In particular, for all those non-negative theta 1, theta 2s, such that theta 1 plus theta 2 equals 1, this is going to be true. So C is going to be convex. And of course, if you assume theta 2 is 0, then it contains this condition. This for any non-negative theta, theta x belongs to C. So it's both convex and a cone. And to answer that question about example of a cone which is not a convex cone, so think of R2. So we are in R2 right now. This is the 0 vector. So this is an example of a convex cone. I can choose another direction. This is an example of a convex cone. But their union, which is the set we're looking at, is not convex because I can take 2 points here and here. This line will not be in here. But if you take any vector in this cone, you scale it, it's just going to be in that cone. So if you take a vector here, you extend it by theta, scale it by theta. So yeah, that's an example of a cone which is not convex, but I just had to give this definition. But all the cones we'll be considering will be convex cones. Those are like really the relevant cones for us.
Sir, it means when we take a union of two convex cones, that is also going to be called as cone, right?
Yeah, right. Generically speaking, because you can have two intersecting convex cones, like let's say this is one and this is one, then their union is again a convex cone. But in general, it may not be so. Yeah. But what you said is correct. Like generally, a cone will be essentially like unions of convex cones. Okay. So with this definition, and let's just write it in word. In other words, C is closed under positive linear combinations. C is closed. So closed, I don't mean in the sense of topology or metric spaces or whatever. I mean in terms of algebraic operations. So the operation is just given by this combination. So closed under taking this linear combination theta 1 x1 plus theta 2 x2. So C is closed under positive linear combinations. That is the definition of a convex cone. Okay. And again, another equivalently, you can see just writing out what this means. Equivalently. So remember, in the previous definition, we had just taken theta 1 and theta 2. But we can, in fact, just by induction, you can show that I can expand it by saying, okay, I can take theta I, theta k, theta 1 to theta k, and x1 to xk, and the same result will hold. So let me just write it out. So equivalently, if you have k vectors, x1 through xk in C, then theta 1 x1 all the way up to theta k xk belongs to C for all these theta i's bigger than or equal to 0. And these type of combinations are known as conic combinations. So remember, first we had linear combinations for subspaces. For affine sets, we talk about affine combinations. For convex sets, we talk about convex combinations. Here, this is conic combinations or positive combinations. We'll summarize all of that very soon. Okay. And similar to how we had defined affine hull of a set, where set may not have any structure, it could just be a discrete set, maybe it's 5 points, whatever. So we had talked about affine hull and convex hull. I didn't talk about linear hull because that is something which is very familiar to you from linear algebra. You take some points or like non-zero vectors. And when I say linear hull, that would mean the smallest linear space generated by these things, by the linear combinations. So our next definition is about conic hull of a set S in Rn. So let S be a subset of Rn, possibly infinite. So in the previous lecture, I had stressed on this in the sense for affine sets, this possibly infinite can be replaced by a smaller set. Like for example, if I gave you infinitely many points in Rn, and said I want to talk about the linear hull, sure, there will be a smallest linear subspace containing all those infinitely many points. But we know that that subspace will have a basis. So we can actually find finitely many linearly independent elements from this set, which will generate that space. So although we may start with infinitely many, but we don't need that information. And the same will hold for affine hulls, but not for convex hulls. And the small example I had given is, if you take a sphere and its boundary, the boundary has infinitely many points, and you take all convex combinations, then you'll get the whole sphere. But you cannot reduce it to a finite set. If you choose finitely many points on the sphere and you take its convex hull, you will not get back the sphere. You'll get back something known as a polytope. We'll look at, in fact, those are the things that are very important to us, polytopes. But I just want to say that this possibly infinite can sometimes be replaced by a finite subset of S, but not always. Okay, so let S be a subset of Rn, possibly infinite. The conic hull of S, also not nothing extremely imaginative going on. It will be the same definition, just there you had convex combinations, here you would have conic combinations of elements of S. So the conic hull of S is the smallest convex cone in Rn containing S. And in the following sense, now this sense is already clear to you what we mean by that. Intersections of cones again, or convex cones again, will be convex cones. So based on that, I can talk about the smallest set. So in what sense? If C prime is any convex cone in Rn with this set, again repeating that this set S may not have any proper structure to it. It may be just finitely many discrete points, or it could even be surface of a sphere, which has a pretty good structure. It's a manifold and so on, but it doesn't have to be that way. So if C prime is any convex cone in Rn with S contained in C prime, then conic hull of S is contained in C prime. And as usual, we'll write out this other definition, which is that this conic hull contains all the conic combinations of points in S, theta k x k, such that xi belongs to belongs to S, sorry. This xi belongs to S, theta I bigger than equal to 0, and I equals 1 to k. So this is the set of all conic combinations of points in S. And of course, like I had said previously, one has to show that this is in fact a cone, a convex cone. Just like there we had to show that whatever sets we had defined for affine hull, for example, we had said this theta I should satisfy the condition that the sum is 1. Then you also have to show this is an affine set. I mean, it's a couple of steps, but still it's not something which you should take as absolutely obvious, because yeah, I mean, here it is defined originally, first of all, using 2 elements, and now we're talking about k elements, and k can vary and so on. So anyway, so you get the point. Yeah. So now that we have all the spaces that we that are relevant to us, linear spaces, affine sets, convex sets, conic cones, convex cones, we just need to define something related to cones, what are known as generalized inequalities. Then we'll circle back to our linear program and tie all of these together. So what are generalized inequalities? So effectively, when you talk about x being bigger than equal to y, real numbers, x bigger than equal to y, what we mean is x minus y is positive. In fact, first of all, you need a notion of positivity. Then you can talk about inequalities. So positivity means x minus y belongs to a certain subset of R, the real numbers, which has some properties. Perhaps in your analysis 1, you have seen those properties. First of all, it has to be additive, and if you multiply a positive scalar, it has to stay within that. That is also an example of a cone. So if you take the real line and this is 0, this is an example of a cone. This is a convex cone, in fact. So once you have a convex cone, you can actually define some sort of ordering structure. It will not be a total ordering. For real numbers, it will give you total ordering. If you give me 2 numbers, then either x is bigger than or equal to y or y is bigger than or equal to x. That may not hold in general, but you can have some sort of partial ordering. So let me define a few things now. A cone C in Rn is called a proper cone. Okay, so proper cone if the following conditions hold. First of all, K is convex, so it has to be a convex cone. And we'll see how the partial ordering depends on these properties. Without these, you may not even have a partial ordering. So K is closed. 3. So K is closed. This assumption is to have good limiting properties. So I want to say if xi bigger than or equal to yi, and I have a sequence, I want to conclude something like the limit x for the sequence xi and limit y of limit sequence yi. I also have this inequality, x bigger than or equal to y. So for that reason, we need this K is closed. So we'll see that. Yeah.
K is the subset of Rn, right?
Right. Sorry. Maybe okay. Since I have written K there, yeah. So cone K in Rn is called a proper cone if K is convex, K is closed. Yeah, K is a subset of Rn, right? Yeah, so K is solid, meaning non-empty interior. And why would we want that? Because, for example, this thing, I can also think of this as a convex cone in R2 also, right? Then I can say two vectors in R2 will be comparable in this way, x bigger than or equal to y, if x minus y belongs on this line. So that will be essentially concentrating on one component of, like, you have two coordinates, so it will be comparing one of them. The rest, it's like it doesn't matter. So you'll get some sort of ordering, but that may not be very satisfying. So that's why we want it to be solid, non-empty interior. Okay. 4. K is pointed. K is pointed, meaning it does not contain any lines in it. So which means it contains only rays. Rays from the origin, but no lines. Yeah, by the way, if you recall the definition, even Rn is a cone in this definition that we have. Because if you take positive combinations of two vectors in Rn, it will lie in Rn. That's kind of obvious. So we want that will not hold, like K is pointed. Otherwise, you will not be, like, everything will be comparable to each other. Like, you will not get anything interesting out of it. Okay. And anytime you have a proper cone, there is actually like a one-to-one correspondence between some partial orderings and proper cones. And how do you get an ordering? A proper cone defines a partial ordering which typically will denote by something like this with a subscript k to denote that this cone is the one which is defining that partial ordering on Rn in the following manner. X, the vector x, is less than or equal to y if y minus x belongs to k. Just like here for the real line case, we had x bigger than or equal to y if and only if. This is the definition, so I didn't say only if, but yeah, but they're like, that's the way we'll define it, that x minus y is a positive number. So here the k is defines the notion of positivity. But of course, just because I defined it this way doesn't make it a partial ordering. We have to use those properties to show that this definition in fact gives you partial ordering. So that I'll leave as an exercise. So today actually I'll post an assignment. So these exercises which I have been mentioning will be part of that assignment. So what is a partial ordering? So there, first of all, you need some sort of reflexivity and transitivity and symmetry. Like if x is less than or equal to y, y is less than or equal to x, then you want x is equal to y. So that is where the pointedness will come in. because if k has this sort of if both x and minus x can belong to k, then essentially both are positive, right? Both x and minus x are positive. So you want to say something like if both x and minus x are positive, that means x must be 0. So for that symmetry, you need this condition of being pointed. So as you go through the check the definitions of partial ordering, you'll realize what all these conditions mean. And of course, you need transitivity, meaning x less than equal to y less than equal to z means x less than equal to z. That means this must have some sort of, like if I take two elements in k, their sum must be also in k. So all these things you will use to prove that this in fact defines a partial ordering. And let's look at a few properties. So if x is less than equal to y, then x plus z is less than equal to y plus z for any z in Rn. This is clear, right? Because if I take the difference, it's just y minus x. If I know y minus x is in this cone, of course, y plus z minus x plus z is also in this cone. Then 2, for any positive scaling, for any alpha bigger than equal to 0, for any scalar alpha, I have this. And that again, because this cone is closed under positive maps, that's the definition of cone we had. If I scale it by some positive number, it should not go out of that. And 3, if xi, there is a sequence of vectors which I already mentioned. If this is true for I equals 1, 2, and so on, and these vectors xi tend to the vector x, and you can just assume that you are using the Euclidean now. Whenever I talk about the metric space structure of Rn, I'll typically use the standard like Euclidean norm. So no confusions there. And let's say yi goes to y, then x is also less than equal to y. There I need that k is closed, because the difference yi minus xi, each of them is a vector in k. So now I have a sequence in k, sequence of vectors in k, and the limit is y minus x. And since k is closed, again y minus x also belongs to k, so y bigger than equal to x. So all the intuitive properties that you want from your partial ordering of vectors is available if you use this sort of code. Okay, so let's see a couple of examples. So 1, k equals r plus equals this interval 0 infinity in R. This is the one I was talking about. So this is the usual ordering, less than equal to on R. Okay, and by the way, these inequalities are known as generalized inequalities. So I'll write ordinary inequalities in R are special cases of generalized inequality. In R are a special case of generalized inequalities. Okay, not very surprising. The second example is what is actually quite important when we come to our linear programming. So non-negative orthant and component-wise inequality. So that's the second example. So what is the non-negative orthant in Rn? So the non-negative orthant k equals r plus to the n, meaning it consists of all those vectors in Rn where all the components, all the coordinates are positive, is a proper cone in Rn. So this is something you can verify. For example, in R2, this is the orthant. So this is r plus and r plus here. So each coordinate is positive. So this is a proper cone. So this partial ordering corresponds to component-wise inequality. This corresponds to component-wise inequality. This is the generalized inequality of vectors. And what it means is if I have x vector less than y, let me just write the subscript r plus to the n to remind you, but later on we'll just assume that if nothing is specified, we mean r plus to the n. So this means xi is less than or equal to yi for I equals 1 to n. These are the coordinates of x and yi's are the coordinates of y. Okay. So with all this notation in hand, we'll come back to LP. So what is the relevance of all this to LP? We will rewrite everything as, so decision space, we will rewrite as AX is less than B. Very nice, succinct manner. So we had all this bunch of inequalities, and yeah, and let's say wherever there is equality, we'll let Cx equals D. So let's split them up for this matter, because remember what I had said like once, that even if I have these equality constants, I can always replace them by inequalities. Like if I had x1 plus x2 equals 1, the example I had given is I can replace it with these two things, and minus x1 minus x2 is less than or equal to minus 1. So these two combined will give me this. So I can always in general write it in this manner, but let's just go ahead and split them up into like the most simplest cases. So ax less than or equal to b and cx equals d. So this is an affine set. We have seen it's a set of solutions to these systems of linear equations are affine sets. So this is in fact a convex set. You can just check if I have ax is less than b and I have let's say y is again less than b, so that x and y both satisfy this, then if I take a convex combination, so k, remember that k is a convex cone, right? It's a proper cone, it's a convex cone. So when I take theta of b minus ax plus 1 minus theta of b minus ay, that is in fact, of course, bigger than the zero vector, right? Because this is bigger than the zero vector, that is in the cone. This is bigger than or equal to the zero vector. So the convex combination also is in there. So this theta b plus 1 minus theta b will again just give you b. The rest will just tell you that a theta x plus 1 minus theta y. So again, this vector. So if x and y are satisfying this inequality, then their convex combination will also satisfy. So this is in fact a convex set. And in order to write it in this manner, so for this, we needed convex cones. And the advantage of writing it in this manner is, remember, when we do linear algebra, we had all these very complicated looking massive systems of equations. But once we write it in matrix form, it looks like you're dealing with just one variable. Like, sorry?
Can you please repeat this part?
You mean this part? Yeah. Okay, so let me erase this and redo this. Okay, so what I'm claiming is, so what is the decision space? It is the set of all vectors satisfying the constraint, set of all x satisfying constraint functions or constraints, right? So let's say x satisfies this constraint. So let's say x1, let me say x1 belongs to decision space and x2 both belong to decision space. So what does that mean? ax1 is less than b, ax2 is also less than b, right? So if you infer what this statement means, this means b minus ax1 belongs to r plus to the n, right? But that is how what we mean by this inequality. And b minus ax2 also belongs to r plus to the n. And actually, this is not the only constraint. We also have cx is equal to d, but that is actually much easier to handle. Cx1 equals d, and cx2 is also equals to this vector d. But we'll handle that later. But we know that r plus to the n is a convex set. It's a convex cone, right? So if I take convex combination of these two vectors, that will again an r plus to the n. So let's say I take theta b minus ax1 plus 1 minus theta b minus ax2. So this also belongs to r plus to the n, right? Are you with me?
Yes, yes.
Yeah. So now I will combine them together. So theta times b plus 1 minus theta times b. What is that? That is just b, right? Theta plus 1 minus theta is 1. So it's 1 times b. That's the vector b. Then this is ax1 plus, so let me take minus common, 1 minus theta ax2. So this is what we have. Now note that A is a linear map. So this theta can go inside, right? That is the definition of linear map. Like not only A x1 plus x2 is ax1 plus ax2, but also A of theta x1, the theta can come outside, the scalar multiplication. So this,
But sir, we could have taken any theta 1 and theta 2 which are greater than 0. That linear combination will also lie in R plus 2 divided.
no, but then will you get b here? Let's say you take theta 1, theta 2. What you will get is theta 1 plus theta 2 times b, right?
Yeah.
So what we want is the end result. Okay, let me just finish this thought, then we'll come back to your question. So then I take the theta inside and 1 minus theta inside. So then I have this. So this is fine. We all agree, right? So I'll take the theta in here and 1 minus theta in here, and then use the fact that a of x plus y is ax plus ay. So you have a of theta x1 plus a of 1 minus theta x2. It's a linear map, so I can do this. So what this tells me is that b is bigger than or equal to a of theta 1 plus 1 minus theta x2. And similarly for cx, you have c of theta x1 plus 1 minus theta x2 is equal to d. Simply because if I take this, what do I get? Theta of cx1 plus 1 minus theta of cx2. What is cx2? That is x1, x2 belong to the decision space. So cx1 must be d, cx2 must be d. So what I get is theta d plus 1 minus theta d, which is equal to d, right? So that's where I got this expression. So from both of them, what I get is if x1, x2 belong to decision space, implies convex combination of x1, x2. So the convex hull of x1, x2 belongs to decision space. So your question was, since it's a cone, I can, why take theta 1 minus theta? I can always take theta 1 and theta 2, where they're both positive. That is correct. But then what you'll get is you'll get a theta 1 x1 plus theta 2 x2 here. Here you'll get theta 1 plus theta 2 times b. Then what do we do? How can I conclude? I'll definitely conclude theta 1 plus theta 2 b is bigger than or equal to a theta 1 x1 plus theta 2 x2. But that does not mean that this element what I get will belong to my decision space, because there is a theta 1 plus theta 2 here, right?
We could have divided by theta 1 plus theta 2.
Yeah. Then once you divide it, what do you get? You get, so if you divide it, you get
Again
theta
in
1.
the same form.
It will be it's just a reparameterization, you can think. So if you think of this as theta, isn't this 1 minus theta?
Yeah.
So it's exactly the same thing. So because I was trying to prove it's a convex set, then I just started with theta and 1 minus theta. So I hope that is clear. Okay. So I'm going to assume, since you didn't reply, I'm going to assume it was clear. Okay. So that, yeah. So yeah, so essentially now we have gotten like all the ingredients. So we have concluded that in fact our decision space is always going to be a convex set. And if you want to write in terms of inequalities and equalities, this is the notation. This is very clean notation. And in linear algebra, in mathematics, actually notation is very important. Like Shakespeare has this quote, right? What's in a name? That which we call a rose by any other name would smell as sweet, right? Romeo and Juliet. But that is not 100% correct. That is correct in some sense. Once you name things, and once you, like, that's the point of having a language, right? You name things and you identify important things, you label them, then it gives you a way to talk about them and draw analogies with other things, right? So here you have Cx equals D. Forget about the inequality part. For now, just concentrate on Cx equals D. So in linear algebra, this notation looks very analogous to what we have for just real numbers. Ax equals b. All I have to do is take inverse of a, multiply on the right hand side. So x must be b over a. So just that feeling kind of tells you how to proceed next. If c is invertible, very good. You try to find its inverse. There are many algorithms, many strategies. Then x is equal to c inverse d. So notationally, these things become very convenient, and you start doing operations, and you start discovering those operations. Like Gaussian elimination and those kind of things. So that is also the advantage of like having all these definitions, is it looks very analogous. This looks like an inequality. This looks like ax less than equal to b, and so on. All right. Okay, so there are two. So one goal I said is to understand the structure of our decision space. I'm not going to claim that that study is complete. In fact, it will take probably this week. It may spill over to the next week. But you can always dig deeper, go down the rabbit hole. So, okay, we concluded that it's a convex set. Can we say something more? And we want to say something more. In fact, we want to say it's something known as a polytope. And how do we represent polytopes? So goal one was for humans to understand the decision space, for us to understand the structure of the decision space. And goal two is to make a computer understand it. So our efforts will in fact be very much geared towards that. Goal one, to understand the structure of the decision space. We want to do that by introducing suitable notation, suitable language, suitable definitions. And goal two is to make a computer understand. So computer can only understand finite things, but we have all these very infinite looking decision space. It's not comprised of some discrete points. So how do we do that? So for that, we have to dig deeper into the structure of the decision space. Yeah. So now we'll recall again some notation and definition. Perhaps for those who actually for most of you, since you have done linear algebra, it might be a bit boring, but please bear with me. I think some of these things like require repetition, so I'll just repeat. So let's take k vectors in Rn. If I write this for lambda I in R, this is a linear combination. So of these vectors. So you start with k vectors. This is what is known as a linear combination. I'm just going to repeat what we have done. Like we have talked about 4 things. So I'm just going to repeat those 4 things like a summary, but with a purpose behind it. Okay. So let's say you have this for lambda I belongs to R. I'm going to add a further constraint. So recall here no constraint, here it's a constraint. This is an affine combination of these vectors. Affine combination. Then 3, as you can guess, is convex combinations. So you have this. So our restrictions are, it has to be positive and sum has to be 1. This is a convex combination. And 4 is what will be a positive combination. So lambda 1. So same expression, just we are varying what the the coefficients that are allowed. So for lambda I bigger than or equal to 0, such that lambda 1 all the way up to, oh, okay, so sorry, here you don't have any restriction. So this is a positive combination. Okay. So then, of course, once we have this, we defined this hull. So let S be a set in Rn. Again, you can very well anticipate what I'm going to write next. Linear hull of S is the set of linear combinations of elements of S. Is the set of linear combinations. It's a linear subspace, okay, of linear combinations of S, or you can say S linearly generates lin S. Lin S is the notation we're going to use for linear hull. So this is important. We are talking about somewhat of a generating set. Like you have like encountered this term, like when you have, let's say, a group, you talk about generators and relations and all. So you want to find a certain like finitary subset which will generate your like the space you care about. So that's why we like want to stress on this definition.
This means span, right? Like span.
Exactly. Yeah, right.
Yeah.
So
Okay.
this is exactly span of S. So yeah, so yeah, I mean that is span is probably more standard terminology, but here I'm just going to use lin S, but that is exactly span of S. Okay.
Okay, sir.
And affine hull of S is, you just replace these words that I've underlined, is the set of affine combinations. So the word you'll probably use here is S affine. I don't know whether there is a real word like that, but let's just pretend there is. Affinely generates Fs. Then 3, convex hull. Of S is the set of convex combinations of points in S. They are convex combinations of points in S, or S, let's say, convexly. Again, I don't know if there is a word, but you can guess what I mean by that. Generates conv A. So conv A is the notation we have been using for the convex hull. And 4, the positive hull, which we'll call pos S. By the way, it's not A. This is S. Did I write A here? No. Okay. So convex. Now positive hull of S, again, is the set of positive combinations. So we have a recipe to combine things, and we want to know the elementary elements, or the like atomic elements, which will combine to form more complex things. Of points in S. So S positively generates pos S, and you can easily see that conv S is nothing but Fs intersection pos S, right? Because what does affine set require? Affine hull require? It requires things to sum up to 1. There is no sign constant on that. It can be positive, negative, doesn't matter. The coefficients here, the lambda i's, they just have to be, they have to sum to 1. In pos, you don't have this condition. All you need is lambda I bigger than or equal to 0. If you combine those two conditions, intersection of those two conditions, you have both of these. So yeah, convex hull is just affine hull intersection positive hull. Okay. So now we can ask the reverse question. We can ask, so given an S, you found the space. You found a convex hull and affine hull, positive hull, a span or linear hull, and so on. We can ask the reverse question. For 1, let V be a linear subspace of Rn. What is the smallest set S such that span S is equal to V? or the smallest generating set, so to say. What is the smallest generating set of V? So what is the smallest set? S. And the reason I put smallest in quotes is because the smallest may not be unique. There can be many smallest things or many minimal elements, so to say, such that lin S or span S is equal to V. So what is the answer to this? Can someone tell me the magic word that you have to use?
Basis.
Basis.
Exactly. So you have a finite basis. Rn is a finite dimensional space. Every subspace is also finite dimensional. So you'll have a smallest spanning set, which is finite. So to a computer, although it will not understand what a subspace is, it is like has too many points, infinitely many points, unless you are over a finite field or something like that. But you can at least represent it using a basis. You can just give some coordinates and then computer will know, okay, this is the subspace. Then I'll ask the second question, 1, 2, 3, 4. We have done it twice. Now again, the question is going to be clear. Let A be an affine set in Rn. I'll write exactly the same question. What is the smallest set S in Rn such that Fs is equal to A? And here also the answer is very similar, because what are affine sets? They're just translates. The only thing is this vector. So all you need is this vector, the translate, and the basis of this space, right? So in fact, if you specify n+1 vectors, affinely independent, I'll define after I have, but it is something very clear from what the definition should be, as it is essentially all those vectors on here, which are linearly independent if you translate it to the origin. So here,
Basis of A minus X naught
yeah, exactly. So you just
plus
have,
X naught.
yeah, plus X naught. So to define a k-dimensional affine set, you have to specify k plus 1 things. One is the translate, and rest as so can you, so who gave that answer? Can you please tell me your name?
Ramakrishna.
Yeah, Ramakrishna. So as Ramakrishna said, so you, to define a k-dimensional affine set, you need k plus 1 things. One is this translate x0, and then you need linearly independent vectors on, once you start pretending it's a subspace, you need that. So the answer is reasonably clear. So something like a basis. So let's call that an affine basis. I'll define it after I have finished this thought. Okay. So things till now is something which is very familiar to. What may not be familiar to is what I'm going to write next. Let C be a closed convex set. If it is not closed, you just close it up and use whatever results you have on there. Yeah. So let C be a closed convex set in Rn. Same question. What is the smallest set S in Rn such that the convex hull of S is equal to C. And here, I mean, this is a result which we'll be doing. Perhaps, like I said, it might spill over to next week, but this is something which we'll try to understand. Like, given a convex set, what is the smallest generating set? Generating in what sense? In sense of convex combinations. And I can give you the answer right now. If, let's say, we are in 2 dimensions and you have this pentagon, then this 5 points can in fact, so the vertices, so convex hull of the set of vertices is equal to this pentagon. And if you take a circle, so here you have 5 points. For the circle, you'll have infinitely many points, but you'll need that. So here you may not have finitely many things, but for a linear program, in fact, we'll have finitely many things. Again, that needs a proof, which is not entirely trivial. So that's what we will be doing. But here you can imagine, like, in order to get things here, all I have to do is take convex combinations of these 2 points. So I just need 2 coefficients. But once I have gotten here, any point here, let's say I just join a line, it has to intersect somewhere. Each of them I have already written as convex combination of two things. Here, worst case, it will be four things. If I'm again rewriting as convex combination of these 2 points, and each of them is convex combination of 2 points. So this is convex combination of 4 of these vertices. So it is not hard to see that for this pentagon, the convex hull of the vertices gives you this. So to specify this convex body to the computer, you can just tell, okay, these are the vertices, finitary information. And although it doesn't know what to do with it, you know how to use this fact to generate this convex hull. Okay, so this is something we'll prove, but this is for bounded closed convex sets, or in other words, from Heine-Borel theorem, you know that closed and bounded in Rn just means compact. So I should just say compact convex sets. This is in general true, that a compact convex set is always the convex hull of its extreme points. I have not defined extreme points, we'll do all that, but you can guess what those extreme points are. Those are like things on the boundary, but not every point on the boundary is an extreme point. For example, this is not an extreme point, but these vertices are extreme points. So what distinguishes these two? So we'll have to figure that out. So that is the finitary information we'll need. And
Sir, is in some time, I mean, in some cases, extreme point is going to be different from the vertices.
no. So the circle example, think of it. There are no vertices per se, right?
Yeah, that's why we have another term.
Yeah. So it will, and in the compact case, no. So it will always be vertices. But what does a vertex mean? So I drew a picture in 2 dimensions. It was very clear what vertices mean. But in like higher dimensions, like how do you specifically infer what a vertex looks like? I mean, you think it's something pointy, but what does pointy mean? So that is something which we can actually very carefully and rigorously define what pointy means.
Can we say it like this, that a point which cannot be expressed as a linear combination of other 2 points belonging to this?
Yeah, I think you are correct, almost correct, but what you want to say as convex combination, as a proper
Yeah.
convex combination of other 2 points. Exactly. So that is one definition of extreme point. There is another definition using something known as supporting hyperplanes, which we'll do. So let's see. That I will reach today. So there are 2 representation theorems which I want to prove for compact convex sets. One of them is using linear inequalities. So when we talked about convex sets, we showed that the decision space is a convex set, and it was defined using linear inequalities. But it is in fact true that any convex set is in fact given by linear inequalities. The only difference might be it might be infinitely many linear inequalities. Like for the sphere, you might need infinitely many linear inequalities. For the polytope, you will need finitely many. But it is an if and only if condition. Convex sets are completely characterized by linear inequalities. So this might remind you something from a theorem from analysis 1 or 2. You have a convex function, which by the way, by definition means whose epigraph is convex. So this region is convex. That's why such a function is called a convex function. So there you might have seen that any convex function is supremum of all these lines. So lines are convex, that is clear. And if you have 2 convex functions, supremum of fg is also convex. In fact, you can show that any convex function is supremum of possibly infinitely many functions on R. I mean on R. So this is the type of theorem we'll show. So these are the boundaries in some sense. These are bounding, supporting like hyperplanes. In this case, these lines are hyperplanes in R2. So my point being, let's take a careful look here. So my point was, you saw that this is a convex set, and the converse is also true. Any convex set has to look like this. Only difference might be you might not have finitely many inequalities. So, and draw analogy with affine sets. So affine sets initially we defined using linear combination. Then we concluded that it is no different from translation of a subspace, very familiar looking objects. So here also our intuition is that for convex sets, we want to build it up using some very familiar objects. All right. So any other questions? Okay, if not, then we'll start talking about examples of those building blocks. I said convex sets can be built out of some very like simple convex sets. So we'll look at examples of convex sets, and proving these theorems will require some effort. We'll do it over the next few lectures. So first, very, very important example, hyperplanes and half spaces. Okay. So what is a hyperplane? It is in fact a affine set, and we have seen affine sets are convex. So hyperplane is solution of one linear equation. So a hyperplane here. So say a hyperplane is a set of the form which we will denote H A vector. A is a vector, B is just a scalar. All those vectors X in Rn such that which satisfy one linear equation, like I said, A transpose X is equal to B, where A is non-zero. Because if A is zero, what happens where A is not equal to the zero vector? So either this is a feasible, like it is empty, like if B is non-zero, then of course, and A is zero, then this is not possible. HAB has to be an empty set. Or if B is zero, then it is the whole of Rn. So that's why we want to exclude this condition A equals zero. Yeah, if A is equal to zero, like I said, there are two choices: either it is empty or whole of Rn. We don't want that, so we choose A to be a non-zero vector. So what exactly does this HAB look like? Like I said, it is solution of one like linear equation. If B is zero, geometrically, how do we think of it? So if B is zero, so it is essentially things, all those X's that A transpose X is zero. This is precisely inner product, right? Inner product of A and X. So it is all those X which are orthogonal to A. So if my vector is looking like A, then it is perhaps in higher dimension, you'll have a subspace which is orthogonal to A. So HAB has dimension n-1. Has dimension n-1. It is something which is orthogonal to this vector A. That is in the case if B is zero. If B is not zero, it is in fact just a translate of such a hyperplane. Okay. So first, let me just write. It's a solution of one non-trivial linear equation, one non-trivial linear equality. So that's the hyperplane. Geometrically, HAB has normal vector A and B determines the offset from the origin. Okay, so let's elaborate a little bit more. I mean, intuitively, geometrically, it is clear, but still we have to mathematically show this. So let X naught be such that it's a solution. Let X naught be a solution to that one non-trivial linear equality. Yeah. So such an X naught always exists. So that is, of course, the first thing to note. If I'm saying that let X naught be such that this is, by the way, did I write? Yeah, okay, so this B is not a vector. So I should write if B is zero, equal to zero. It's a scalar which is equal to zero. Yeah. So let X naught be such that this is such an X naught always exists. So why so? Can someone give me a quick answer? So why should such an X naught exist?
The A is non-zero, right?
Yeah, A is non-zero, yes. Yeah, I mean, all you have to do is just choose the corresponding coefficient. So essentially it's like
B by A and others zero.
Yeah, right. So X naught, you just put everything else zero, take a non-zero coefficient in A. So essentially coordinate wise, you just do that. You have an equation ax equals b where a is not 0. So you just put x equals b over a. So it's as simple as that. All right. So such an x naught always exists. And then HAB you can express as, so then HAB is nothing but x belongs to Rn such that x minus x naught. Remember this A transpose x naught is B. So this I can write as x is 0. So once I translate this x, it is going to be orthogonal to A. So that is precisely like showing why this holds true. HAB has normal vector A and B determines the offset. Okay. So this just tells you that x minus x naught is perpendicular to A for all vectors x in HAB. So this x naught gives you the offset. All right. So that was about the hyperplane. So hyperplane doesn't, it's an affine set, doesn't have to go through the origin and so on. The next thing is a half space. A closed half space. So here when I say closed, I mean in the sense of topology or in the sense of metric spaces. A closed half space in Rn is a set of the form so HAB minus is the notation. It's all those x's such that in the previous case hyperplane we had an equality, but here we have less than equal to. Okay, there's no. It's less than equal to B. And as you can guess, the other side is known as H plus, is bigger than equal to B. And of course, the intersection of this H minus and H plus, these both closed half spaces, is the hyperplane HAB. So what does that look like? So you have this hyperplane.
Would you please explain the definition of hyperplane once again?
Yeah. So hyperplane is essentially solution to one non-trivial linear equation. So this is the definition. It's all those x's which solve this equation. So if A, for example, was the vector A1 up to AN, the column vector, so this is your A, then essentially it is consisting of all those x1, x2, xn such that this holds. So it's a solution to this equation, right? And so the solution set thought of as in column vectors, right? Now geometrically, if you think of it, so here what I said, there is a solution to this equation, A transpose x naught equals to B. So take that particular solution. So I'm going to rewrite like this equation equals B as equal to A transpose x naught. I'll choose this particular x naught. From that, we got this expression. From one particular solution, I'm rewriting B as A transpose x naught and then moving it to the left. So then I have A transpose x minus x naught. But what is this expression? I have two column vectors. One is A, that is fixed. X is supposed to be like varying. So x minus x naught is another vector. And this is precisely the inner product, right? It is the inner product of these two. And I'm saying the inner product is 0. And remember, inner product is what? It is just A dot B. If I have two vectors, then it is norm of A times norm of B times cosine theta. So if angle is 90 degrees, then their inner product is 0 and vice versa. Does that make sense? So from this expression, we conclude that any hyperplane is effectively a translation. It's the set of all spaces which are orthogonal to this vector A, possibly translated from the origin by this amount of x naught. So just think of A as being the normal vector, like it is HAB is essentially all those vectors which are orthogonal to A, modulo some translation. So does that make sense? Or can you tell me exactly where you are like missing the point?
Yeah, sir, I got it.
Okay. Yeah. So you can just think hyperplane is like one dimension lower. If you're in Rn, hyperplane will have dimension n minus 1 because you have one constraint. So that will reduce one of your dimensions, one non-trivial constraint. And this hyperplane is essentially serving as a boundary between two half spaces. If you think in two dimensions, this is a hyperplane. This y-axis is a hyperplane, right? It is just given by the equation x equals 0. So this is the hyperplane, and it is dividing your space into two half spaces. So these are HAB minus and HAB plus. Of course, this very much depends on A and B. If I changed my sign of B, replaced with a minus B, then of course what is minus H minus what is H plus will change. But given A and B, this is a well-defined object, HAB. So here, so these are half spaces, and half spaces have the same dimension as your original space. They are a proper subset, but they have the same dimension. Okay, so yeah, this is your hyperplane, and let's say this is your A. So this side corresponds to HAB minus, and this side will correspond to HAB plus. Okay. Again, I didn't specify here, but it's the same, like A is not equal to 0 and B is a scalar. Okay, and one thing to remember is hyperplanes are affine set, but half spaces are not. Half spaces are convex, but not affine. But as you can see, linear inequalities, a single linear inequality. So let me just explicitly write out that solution set of one non-trivial linear inequality. Hyperplane was when we had equality. So these are like the very simple objects, like the basic objects, like the building blocks, like I will say, for our convex sets. And again, let me just write out this hyperplane HAB is nothing but intersection of these half spaces. So that forms like the boundary line for each of these closed half spaces. The boundary of HAB plus and also of HAB minus is the hyperplane HAB. Okay, and as you can imagine, like if I remove this like this equality and just talk about strict inequality, that will give me the interior of this thing. So that will be what is known as open half space. So interior of HAB minus is, and similarly for HAB plus, is called an open half space. We're just excluding the hyperplane out of it. Okay. And I already mentioned this, but let me write it out. So in a certain sense, of course, when I say in a certain sense, once I have done that theorem, you will be clear, okay, what that sense means, but now it is going to be hard to explain. So in a certain sense, hyperplanes and half spaces are building blocks of convex sets. Are building blocks of our decision space. Okay, so remember, what are we doing right now? We are talking about examples of convex sets. So hyperplanes and half spaces are the first class of examples. So let's look at the second class. These are known as polyhedra. A polyhedron is defined as the solution set of a finite number of linear equalities and inequalities. So there we had one non-trivial equality for hyperplane, one non-trivial inequality for half space. Polyhedra is like, okay, I'll take multiple of equalities and multiple of inequalities. Whatever like space I end up with, that is known as polyhedron. So polyhedron is defined as the solution set of a finite number of linear equalities and inequalities. So here I just denoted by P. It's all those vector such that AJ vec transpose X vec is less than or equal to BJ, J equals 1 through some M, and here you have CJ transpose X equals DJ, J equals 1 through P, and here AJ is not equal to 0. Is not equal to 0. Okay, so I mean, you are essentially taking multiple equalities, inequalities, and whatever the intersection of that. So essentially, if you took two half spaces, so recall the pentagon example I had mentioned, that's a convex set. In fact, it's a polyhedron. And it is in fact intersection of these half spaces. So this half space intersection, you can imagine, I'm taking these lines and look at, okay, so let me, so instead of a pentagon, let me take a square. So to make it less messy, or perhaps even a triangle. So think of a triangle and look at these normal vectors. So corresponding to that, there is a half space here. So of course, corresponding to this vector, there is a much bigger half space. But if you take intersection of all these half spaces, what you end up with is a triangle. So this triangle, it can be described, it's a polyhedron. So it's a polyhedron and described by a linear set, by a set of linear equalities and inequalities. I mean, in this case, it will just be a set of 3 linear inequalities. Okay, so described by 3 linear inequalities. For pentagon, you might need okay, anyway, so so for pentagon, you might need 5 linear inequalities and so on. Okay. Yeah, and going back to our decision space, we had all this nice notation and we wrote it in this manner: AX then B and CX is equal to D. Here, by the way, we have a vector. So there we had these BJs were scalars, but we put them together in a column vector form. So B will belong to Rm and D will belong to Rp. So that is the number of equations we had, and A is an M by N matrix and C is a P by N matrix. Okay. So a few remarks about polyhedra. So first, a polyhedra is the intersection of a finite number of half spaces and hyperplanes. Simply because the way it's defined is, it's like and, it is given by an and operation, right? It has to satisfy this and this in linear inequality and this linear equality. So it will be the intersection of a finite number of half spaces and hyperplanes. So now we have a new name for our decision space. Initially, we said that every decision space is a convex set. Now we have a new word for us. So we'll say every decision space is in fact a polyhedron. So affine sets are all polyhedra. And one thing to also note is that polyhedra are closed convex sets. Closure becomes, so that's simply because all these half spaces that we considered were closed half spaces, and like these hyperplanes were also closed. So if you are wondering why so, let's do a quick proof. So how is a hyperplane defined? it was defined something like this, right? Equals b. So if I have a sequence of xi satisfying this and xi tends to x, so I have a, sorry, by the way, this is, I'm always writing this with a vector sign. Yeah, so I have A transpose X, or inner product of A and X equals B. The fact that inner product is continuous is being used here. So if xi tends to some x, and all of these xi satisfy this equation, equals b, then in the limit also you'll have this equation being satisfied. So A transpose X is also equal to b. So hyperplanes are going to be closed, and similarly closed half spaces, the way they're defined again will be closed. So polyhedra are closed convex sets. So, and the closure becomes important when we try to solve the linear program, because remember a theorem from like the metric space theory you learned in analysis 2, that if you have a continuous function on a compact set, it will attain a maximum, it will attain a minimum. I mean, the range will be bounded, and whatever the maximum minimum is in fact attained in that compact set. So for those type of things, we want to have some sort of compact polyhedra. Not all polyhedra will be compact, because affine sets in general are not going to be compact unless it's just the point. Points are, by the way, affine sets, because origin is a zero-dimensional linear subspace. You translate it, you'll get some points. Points are affine sets, so those are compact, but rest of the affine sets are not going to be compact. But in order to even show that you can minimize a given function, or even like a maxima or minima exists, we need some sort of compactness. So this closure comes in handy. Okay. So with this point of view, a quick definition: a bounded polyhedron. So affine sets don't count here; they're not bounded unless they're a point. So bounded polyhedron is said to be a polytope. So what do I mean by bounded? Essentially, it means that I have a big sphere which contains that set. So bounded in the metric sense, and I'm using the Euclidean metric on Rn. Okay. So far we have just been like defining, restating, like those type of things. We have not really proved much results, but that's fine. We're going to get into that territory very soon. We have established who the actors are. So what's the drama that's going to happen, that we'll see very soon. Okay, so quick comment about relevance to LP. I said it verbally, but let me just write it down. So the decision space of a linear program is a polyhedron. If the decision space is a polytope, by some means you can show that decision space is a polytope, that means it's a bounded polyhedron, then you know that objective function, so existence of a minimum or maximum of the objective function is guaranteed. Then it just becomes a matter of finding that point. And in fact, since our objective functions in the beginning, or at least when we are talking about linear programs, is linear, you can imagine that if our space is not bounded, it's not going to attain, like either it is going to miss out on a maximum or it is going to miss out on a minimum, because either it's like a constant or it is going to keep on increasing in a given direction. So one key question is, like, given a system of like linear equalities determining the decision space, can we conclude whether it is bounded or whether it is non-empty? So these are kind of questions we might want to answer looking at those numbers. The computer can like store all these numbers, but what like steps should we take so that it will give a final answer saying, okay, this decision space is empty? Like all these linear equalities and inequalities cannot be satisfied. Like for example, if I give a decision space which looks like this and less than equal to -1, of course it is going to be empty. But is there a way to say that? Or perhaps it is going to be all of Rn. Then you don't have a minimum or a maximum for any objective function unless it is the zero objective function. So these type of questions is built in to study of the decision space. So now you might be able to appreciate why we are spending so much time. We could have dived immediately into simplex method. It's just an algorithm, bunch of steps, and we can always crunch some numbers and figure it out. But we didn't do that. And the purpose is we want to understand the decision space as much as possible so that we can answer such questions. When is it bounded? When is it feasible? When is it non-empty? And what is the minimal way of representing it? And so on. Okay. So remark. So as a general principle, we want to minimize convex objective functions on a convex decision space. So remember, in the first lecture, when we are not really talking much about the math, just about the general territory this occupies. So there we had said that linear programming has very efficient algorithms, but it was realized that they can actually, not just for linear objective functions, but the right replacement of linearity is convexity. You can have very efficient algorithms, very effective algorithms. So we had used that word effective algorithms to solve such problems. And I had also even mentioned a quote where he said it's not a matter about linearity and non-linearity, but rather about convexity and non-convexity. So the hardness of these algorithms is based on that. So we will make an effort to understand general convexity, not just polytopes. So polytopes will come out as a special case, but we'll make the effort to understand general convex sets in Rn. Because the effort is not much more involved. So why not just spend an extra hour and learn about general convex sets? Such problems. So why not understand general convex sets in Rn? All right. So with this question, we'll start with a theorem. So long, many definitions. Now we get a theorem. I mean, not a very complicated one, but still a result. So let's take a break of about 5 minutes, and then I'll be back. Okay, so let's resume. So one of the results we want to prove today is known as Carathéodory's theorem. So short definition. It's about affine independence. So when we're talking about like finding these minimal generating sets, so then we had not really talked about what an affine basis really means. So here it will be clearer. So if x1, x2, xk in Rn, so these are said to be affinely independent if none of them is an affine combination of the others. If none of them can be generated by the others, so to say, is an affine combination of the others. Okay, or in other words, actually I should say in other notation or something, because we're using less words in this equivalent expression. So in other words, if summation I equals 1 to k lambda I xi is equal to 0 with lambda I in R, and summation I equals 1 to k lambda I is equal to 0, then lambda 1, lambda k all must be 0. So you might be wondering, why don't I have a 1 here? Whenever I'm talking about affine combinations, I usually have this, but typically it just means this. So if I'm writing x as, or let's say x1 as lambda 2 x2 all the way up to lambda k xk, let's say, like without loss of generality, that you are able to express x1 as a affine combination of these two. What this means is you want to write this as this coefficient sum up to 1, then there is a coefficient 1 here. So if I move everything here, I'm effectively saying I can write this as 1x1 plus minus lambda 2x2 minus lambda kxk is 0. So, and the sum of these coefficients is in fact 0. So that's why, like, you don't see a 1 here, you in fact just see a 0 here. So that is what affine dependence independence means. And another equivalent way to think of it is if you take these vectors, x2 minus x1, x3 minus x1, all the way up to xk minus x1. These are k minus 1 vectors. These are linearly independent. It is exactly the same as saying that. And if you think of the geometric picture we had a translate, that is our x1. Rest of them, they are linearly independent of the subspace. So x2 minus x1, x3 minus x1, and so on. So that's what affine independence means. So here we have Carathéodory's theorem. So this says that if S is some set in Rn and X belongs to convex hull of S, so that means I can represent X as a linear or a convex combination of elements of S. But how many do I need? So that's what Carathéodory's theorem is answering. I want to do it in the minimum possible way, in the sense, if I can get away with convex combination of 10 vectors in S, 10 points in S, I prefer that rather than using 1 million. So Carathéodory's theorem says that we can always do it with n plus 1 affinely independent points. So then X is a convex combination of affinely independent points of S. In particular, because you can imagine that since the dimension is n, there cannot be more than n plus 1 affinely independent points, right? Here we saw, if I take this difference in Rn, so if I had k elements, I have k minus 1 of these vectors. And since the dimension is n, k minus 1 has to be less than or equal to n, which means k has to be less than or equal to n plus 1. So in particular, X is a convex combination of n plus 1 or fewer points in S. Fewer points of S. So in view of this theorem, you can in fact redefine what convex hull means. Convex hull was like it contains all convex combinations. So you can just say that it contains convex combinations with at most n plus 1 elements, and you'll get exactly the same set due to Carathéodory's theorem. So let's look at a proof. And all of these proofs are very nice because they use tools that you have already learned in your analysis courses and metric spaces and so on. Okay, so let's go through this. So first of all, X is a convex combination. So I can always write it in this manner. I equals 1 to k lambda I xi, where this xi belongs to S and lambda I is strictly bigger than 0. And summation I equals 1 to k lambda I equals 1. Strictly bigger than 0 is if it is 0, you just discard that. Don't keep that term. And let k be the minimal such number. Of course, the claim is not that the xi's will be unique for that minimal k, but what you want to say is it is not possible to write x in this manner where for k minus 1. You cannot have k minus 1 vectors where all these lambda i's are strictly positive and sum to 1, and you have this. And k cannot, of course, be lower than 1. It cannot be 0. So there is such a number. Okay. So assume first that x1, xk are affinely dependent. So the claim is that actually this will lead to a contradiction. They have to be affinely independent. Okay. So assume they're affinely dependent. So there exists alpha 1, alpha k in R, not all 0. And sum of these alpha k's is 0, such that summation alpha I xi, I equals 1 to k, is 0. So that's what affine dependence means, right? So of course, if all of these are 0, then this linear, this affine combination is, or this linear combination is going to be 0. But affine dependence means you can choose non-zero such things, so not all 0. Okay. So choose m such that alpha m is bigger than 0. So this you can do without loss of generality, just one of them. So the mth alpha I is not 0. So choose m such that this holds, and okay, it's not just alpha m is bigger than 0, and lambda m over alpha m is minimum possible from those m's. So you identified all those non-zero coefficients. From amongst those, you compute lambda m over alpha m. This is well defined because alpha m is not 0. So from that, you make sure that lambda m over alpha m is minimum such. Now I'm going to rewrite x in this following manner. I equals 1 to k, lambda I, lambda m. So here m is a fixed number. I's are changing from 1 to k, alpha I, xi. So why is this expression true? Simply because you have, so x is definitely, if you forget about this term, like negative of lambda m over alpha m, then you know that x is equal to summation I equals 1 to k, lambda I xi. But here, when you look at this term, summation alpha I xi, this is precisely where using this fact that xi's are linearly dependent. And this is just a fixed constant. Lambda m over alpha m is just a fixed constant, like the index m we chose appropriately so that alpha m bigger than 0. And amongst those m's, lambda m over alpha m is minimum possible. Or you could just say m says that lambda m over alpha m is minimum possible with the condition that if alpha m is 0, lambda m over alpha m is infinity. So either way, it's just a matter of language. Yeah. So this is true. But what happens when I put in I equals m? Lambda m minus lambda m over alpha m times alpha m. So this becomes 0. So I have, in fact, been able to reduce the number of xi's I need by doing this. So at least one of the coefficients is 0. The mth coefficient is 0. So this contradicts the minimality of k. This contradicts the minimality of k. You are able to like one of these coefficients, so k minus 1 things, you are able to find k minus 1 of these vectors so that x is convex combination of this. Oh, yeah, and another thing we have to check that these are all positive, right? So that's why we chose lambda m over alpha m to be the minimum such. So these coefficients, let me erase this. Previous page. Okay. So here we have lambda I is bigger than or equal to lambda m over lambda over alpha m times alpha I. That because simply if alpha is 0, since lambda I is strictly bigger than 0, this holds. If alpha is not 0, we have lambda I alpha I is bigger than or equal to lambda m over alpha m if alpha I is not equal to 0, because that's how we chose this, right? It was the smallest possible such thing. So this inequality always holds true. So which means this difference is always bigger than or equal to 0. So what about the sum? First of all, the sum of this, the first term is 1. So I have lambda m over alpha m because lambda i's were the ones determining that convex combination. Times I have summation I equals 1 to k alpha I. Now look at this. What do we have here? That sum is equal to 0. So in fact, these are coefficients. So these are all positive and they sum up to 1. So in fact, this is again a convex combination of these xi's with this point that one of the coefficients in fact is 0 when I equals n. So that's why we have been able to reduce this value of k. Okay, so we had to check this. So let me rewrite that. So at least, so lambda m minus lambda m over alpha m is equal to 0. So contradicting the minimality of k. And why did we get this contradiction? That's because we assumed these xi's are affinely dependent. That's where all this trouble started. Okay, so that must mean that if we choose that minimal such k, then all of these must be affinely independent. So that finishes the first part. So if we look at this theorem statement, if S is an Rn and X belongs to convex hull of S, then X must be a convex combination of affinely independent points of S. And then we noted that how many affinely independent points you can have in Rn, that's not more than n plus 1. So as a corollary, what you get is, in particular, X is a convex combination of n plus 1 or fewer points of S. So you can choose these points to be affinely independent. So n plus 1 or fewer affinely independent points of S. Okay, so this is QED. So now this brings us to a definition which is going to ring a bell, a K-simplex. So till now we have talked about the simplex method, but never really defined what a simplex is. A K-simplex in Rn is the convex hull of k plus 1. So k represents the dimension. That's why here we have a k plus 1. So k plus 1 affinely independent points in Rn. Of course, you cannot have a n plus 1 simplex in Rn. You can at max have a n simplex. Triangle is going to be a 2 simplex. Yeah. So yeah. So k represents dimension of the simplex. Of the.
Can you explain this case simplex?
Yeah, K-simplex. Okay, I think a couple of pictures will help. Let me finish this definition, then I'll show. So these points, these affinely independent points are called the vertices of the simplex. Are vertices of the simplex. Okay. So let's say you have 3 points like this. Then, of course, there will be an affine hull. You'll get a linear thing. Let's say the 0 is here. So these are 3 points. And when can I say they're affinely independent? So I fix a point and I take these 2 vectors. So in R2, are these 2 vectors linearly independent? The answer is yes, right? These 2 vectors are linearly independent in R2, which means, so let me call this x1, x2, x3. So x1, x2, x3 are affinely independent. Of course, you might wonder, then I was talking, why am I talking about these 2 vectors? Why not about this vector and this vector? The thing is, it doesn't matter. Like if these 2 vectors are linearly independent, rest of them will have to be. So if you look at the definition of affine independence, it will turn out to be the case. Perhaps an exercise for you, not as an assignment, maybe you can think about it. Yeah, so here x1, x2, x3 are affinely independent simply from the fact that if I fix this vertex and take these 2 vectors, they are linearly independent. So here I would say this is a 2 simplex. So this triangle right here, this shaded triangle is a 2 simplex. Why so? Because I have 2 plus 1, that is 3 affinely independent points, and it is a convex hull. And these 3 points are the vertices of the simplex. That's what the definition means. So let's go in higher dimension. Let's embed this R2 in R3. So then again, this is a 2 simplex. But then if I take a tetrahedron, let's say this base is this triangle, and then I'm looking at this tetrahedron here and then here. Now these 3 vectors are linearly independent, right? So I have x1, x2, x3, x4. So those are affinely independent. So this is this tetrahedron. So triangle, non-degenerate triangle is is a 2 simplex. That's the dimension of whatever is inside. And this tetrahedron, non-degenerate, is a 3 simplex. In fact, generally a simplex, there are many ways to define a simplex. So generally you can think, here I'm making a translation independent, in the sense if I move this around, it doesn't matter. Again, whatever x1, x2, x3 I'll get will be finally independent. But I have the option to fix this at 0. So let me fix this at 0. So this will be so this line is a 1 simplex, this line segment. This is a 2 simplex. Now, if you can imagine this third direction, so this solid thing is a 3 simplex, and you can build simplexes. So otherwise, you can define a simplex in this manner. Simplex is purely x1 plus x2 xk less than equal to 1, x1 bigger than equal to 0, xk bigger than equal to 0. So what happens? This is what is the equation of this line? This is x plus y equals 1, let's say. So then k equals a 2 simplex, right? This is a 2 simplex, x1 plus x2 less than equal to 1, x1 bigger than 0, x2 bigger than 0. That is a 2 simplex, and the vertices are these 3 points. In general, a k simplex can be given by this modulo some changes. Like I can of course multiply some matrix and skew the directions. Instead of angles being 90 degrees, I can change things around. That is fine. But generally a simplex will look like this. So is it clear what a simplex looks like? Like a k-dimensional simplex, what it looks like? It will be like it will look like this. Of course, you are able to twist and skew a little bit here and there. So whoever asked the question, can you just tell me if that was clear enough, or any particular point
Yes,
that
sir,
was
yes.
okay? Yeah. So what does Carathéodory's theorem tell us now in terms of this?
Sir, then a four simplex is and more 4 simplex, 5 simplex. Those are imaginary things, like hypothetical.
So it depends on what you think as imaginary, because 5 simplex cannot be put in 3-dimensional space, but it can be put in a 6-dimensional space or even a 5-dimensional space, right? So so I always said k simplex in Rn, there k has to be less than or equal to n. Otherwise, like you will not even have k plus 1 affinely independent points to define that simplex. So when you talk about a 5 simplex, so 5 simplex can be put in R5 or R6. So I wouldn't really say R5, R6 are imaginary. I mean, especially when you deal with high dimensional data, and let's say you have many parameters. So if these are your decision variables, for example, of course, then R5 is a very concrete object. It's not a very abstract object. It's a very concrete object. So yeah, I'm not sure if I agree with that word imaginary. So, but if you're thinking in terms of physics and all that thing, then R3 perhaps, or you're talking very classically, not talking about M theory or string theory or something like that, then yeah, I mean, then you can say, okay, these are something which are hard to geometrically visualize. So in that way, it is not concrete. It's hard to visualize geometrically, but these objects exist, and I have already given you a list of equations which will give an example of that. Okay. So what does Carathéodory's theorem say in this respect? It states that the convex hull of S is the union of all simplices. So you can build any convex set by joining simplices with vertices in S. Yeah. I mean, for example, the pentagon. What are the simplices? You just take these points. This is a simplex. This is a 2 simplex. This is a 2 simplex. This is a 2 simplex. So you just join them together. What you're getting is a pentagon. So that is the convex hull of these 5 points. So Carathéodory's theorem is essentially telling you that you can, you can represent convex hull of S as the union of all these simplices with vertices in S. Here the vertices are these 5 points, and all these simplices consist of consist of like 3 tuples from S. Okay. So that was the first result, and here we are hearing about this word simplex for the first time, and we'll encounter it again when we try to solve the linear program. In fact, that is known as the simplex method. If you have read ahead, you have probably seen that. Okay. The thing I wanted to end with is the two main representation theorems of convex sets. But let me just, I'll revisit it. So we don't have enough time. There's just 10 minutes left. So, okay, so let me just intuitively tell you what this is. So let's say this is, doesn't look like a convex set, but let's say it's a convex set. Maybe I should try to make it look like a convex. Okay, so let's say it's something like this. This is a convex set. So you have a point here. Let's call this X. So you can think of a hyperplane passing through this, right? So if a hyperplane does not intersect K, it is like there is a half space which contains this space K. So this is called a supporting hyperplane. We'll give very concrete definitions in next class, but for now, let us get the intuition. So it's a supporting hyperplane. Like for this triangle, if I take this line, that's a supporting hyperplane. So I can hear some. I think someone is unmuted and I can hear some noises. Okay. Okay, so this is a supporting hyperspace. Even this is a supporting hyperspace. Through this vertex, this line is a supporting hyperspace because there is a half space which contains this convex set. So such points, like hyperplanes or half spaces are known as supporting hyperplanes. So supporting half spaces for a convex set. And of course, one has to show that given any point on the boundary, you can find such a supporting half space or hyperplane, proving that, like, especially in higher dimensions, where our intuition may not work as well. So there we need to like give a proof or a strategy to see why that is true. So that again we'll do in next class. But it is intuitively clear, like that should be something like this. Like a convex set has something like a positive curvature. It cannot go something like this. It cannot have negative curvature, so it has to curve inwards. So if I zoom in, like take a telescope or microscope, depending on where the convex set is, and I zoom in and I look at this point, then I say, okay, sure, I can draw this tangent type of line. If it's a sphere, I can definitely draw a tangent, but if it's a polytope like this, then I have some freedom of movement. I can do this or do this. All of them are supporting. Yeah, but if you take this tangential thing, then this half space will contain this convex object because there is a positive curvature. Okay, so assuming that, there are two main representation theorems for closed convex sets. Theorems for closed convex sets. So representation theorem 1. So we'll end the class with the statements. Each non-empty closed convex set in Rn, doesn't matter if it looks like a triangle or like a half triangle. It could look something like curved here, but straight here, and so on. It can be any closed convex set. Is the intersection is, I should say, precisely the intersection, not contained in, but is precisely the intersection of its supporting half spaces. In the context of decision space, what I mentioned, we had shown that the decision space is a polytope, and we can give finitely many equalities and inequalities to determine that decision space. Here I'm stating a converse of that. I'm just saying that that was a convex set. So using half spaces, intersection of half spaces, we had constructed a convex set. Here I'm saying any closed convex set in Rn is the intersection of like a family of half spaces, and that may be infinite. That doesn't have to be finite. An example was a sphere. If you take all the tangent like spaces to the sphere in R3, then those will be the supporting half spaces. But for all closed convex sets, that is true. So that is representation theorem 1. And representation theorem 2 is what is known as an extremal representation. So extremal representations. So here, and there are other parts to it. So let me just state the simplest part to this. Each bounded closed convex set, or you can say compact convex set in Rn is the convex hull of its extreme points. So there is a way to define using linear equalities, inequalities, so that is supporting half spaces, and there is a way to define it using convex hull of certain points known as extreme points. Then, so I said I only gave part of the representation theorem 2. That's because I have included this adjective bounded. In here, there is no bounded. I just said non-empty closed convex set. So in fact, if you remove bounded, you can say that either it is, there are some building blocks. Building blocks are linear subspaces. Those are not bounded. Then you have cones. Those are also not bounded. And then you have this. So you can write it as a direct sum of such things. So anyway, we'll look at the most general result. So at the end of this whole circle of ideas, I hope what you'll feel is like you have understood convex sets. Doesn't matter bounded or not. It could be like non-compact and so on. So anytime you think of closed convex sets, you have a very nice, pretty picture. You know all the building blocks and you know how to generate them. For example, if the extreme points are finite in number, it turns out for polytopes that is true. That also needs a proof. How did we define a polytope? Those were intersection of finitely many hyperplanes and half spaces. Then we have to define extreme points and show that in fact that will lead to finitely many extreme points. And the simplex method will start with such an extreme point or a vertex of the decision space, or what they call the basic feasible set. So that's why like we need a lot of control over how these things are interacting, how the half spaces, the extreme points, and all of these are interacting. We need a good idea. And that's what we'll do next class, and if necessary, even next week. So are there any questions? Yeah, I mean, maybe I'll just add a remark, draw analogy with basis. So this is not quite basis, but basis generates or spans the linear subspace. So that's the way you should think. Extreme points will span the convex set. So to a computer, either you can give this finitely many inequalities, or you can give the extreme points, and it will remember at least the shape of that convex set. All right, so if there are no more questions, we will just resume next class, actually rigorously defining what supporting half spaces, hyperplanes mean, and then proving all these results. So see you on Thursday then. Bye-bye.